Relativistic momentum. This video introduces the changes in Newtonian mechanics that are necessary as a result of the postulates of relativity. We will have to modify the concepts of total energy and momentum. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It is very important for the continuity of this channel. So far, we have dealt with the consequences of relativity for ideas about space and time. Since length and time intervals need modification because their value depends on the reference frame from which they are measured, we also might expect that other physical quantities such as momentum and energy need some modification according to the theory of relativity. In Newtonian mechanics, we know that if we push an object that is free to move, it accelerates in accord with Newton's second law. But Newton originally wrote the second law not in terms of acceleration, but in terms of momentum. In accord with the momentum version of Newton's second law, push an object that is free to move and we increase its momentum. As we can see, a body subject to constant force F will have speed v, which increases without bound when t increases, but v cannot exceed c. Newton's formula, although an excellent approximation for small speeds, must be wrong. As we can see, the relativity of space and time requires new definitions for energy and momentum. To find a relativistic expression for momentum, we start considering a particle moving with constant speed v in the positive direction of an x-axis. Classically, its momentum has magnitude given as follows, in which delta x is the distance it travels in time delta t. But you have learned that delta t is measured differently in different inertial frames. So, whose delta t should we use? In practice, it is usually more convenient to work with the proper time because the proper time is an invariant. All observers can read the particle's clock, and at all times they must agree on what this clock says, even if your personal watches are showing different times. We can rewrite this momentum definition using the proper time as follows. This is the relativistic momentum equation of the particle. V is the speed of the particle in a reference frame, and gamma is the Lorentz factor. For a particle of mass m and with a speed v measured in the observer's initial frame, its relativistic momentum is defined as follows. Before continuing, we should stop to talk about the mass of the particle. In older textbooks, the relativistic momentum is rewritten as follows. If we write that way, we could be led to think that a rapidly moving particle undergoes an increase in mass. If we plug the last expression into formulas like kinetic energy, we obtain formulas that do not agree with experiments. Also, be careful not to think a mass acquires more particles or more molecules as its speed becomes very large. It does not. Moreover, m is the mass of the object as measured by a person at rest relative to the object. When a mass is moving relative to an observer, the only way that its mass can be determined is through collisions or other means in which momentum is involved. Since the mass of a moving object cannot be determined independently of momentum, the only meaningful mass is rest mass. Therefore, m here stands for the rest mass of the particle and is a constant for all observers. Let's see how it works. To solve item A, first we find the Lorentz factor. We can see that the momentum is almost 6 times its classical value. We now substitute values into the equation. To solve item B, we find the Lorentz factor as well. So the momentum is less than 1% greater than the classical value. We now substitute values into the equation. To understand the relativistic energy from my approach in this video, you have to know what the space-time interval means. If you don't know anything about this topic, watch the video on this topic before continuing. If momentum needs to be modified to fit with relativity as we just saw in the equation above, then we might expect that energy would also need to be rethought. We start from Newtonian mechanics again. The following formula relates the kinetic energy and momentum. This suggests that a relativistic expression for energy will likely involve the square of the momentum and the mass of particle as well. We now begin the hard work. Energy, like momentum, is a conserved quantity both in Newtonian mechanics and in relativistic mechanics. So let's begin with an invariant quantity, that is, a quantity that is the same in all inertial frames. This quantity is the space-time interval. Let the space-time interval of a particle of mass m moving through the distance delta x during a time interval delta t as measured in frame S given as follows. The space-time interval is invariant. We can turn this into an expression involving momentum if we multiply by mass divided by proper time square. We rearrange the terms and we use the formula for momentum. And we get the new expression with momentum square. The time interval delta t in frame S is related to the proper time by the time dilation formula. With this change, we obtain a new expression. We now multiply by c squared. Finally, we can find the invariant of the right side by evaluating it in the particle's reference frame, because in this frame the particle is at rest. So the momentum is 0 and the Lorentz factor is 1. So the invariant is mass times c squared. We rewrite the last expression to get the energy-momentum relation. If we see the units involved in this equation, we note that mass times c squared is joules. That is the same unit of energy. So we are dealing with energy. We rewrite this expression again. We now will analyze the expression on the left-hand side. Let's see how this expression behaves in low speed limit using the binomial expansion. The second term on the right is the expression for the kinetic energy, but the first term on the right suggests that the concept energy is more complicated than we thought, because it appears there is an inherent energy associated with mass itself. The left-hand side is called the total energy of the particle. The first term on the right is called the rest energy of the particle. And the second term is the kinetic energy of the particle. So the total energy to rest energy plus kinetic energy. The equation that relates the total energy to the relativistic momentum is given as follows. Often the momentum or energy of a particle rather than its speed is measured. So it's useful to find an expression relating the total energy to the relativistic momentum. When the particle is at rest, P equals 0. In this special case, the total energy equals the rest energy. For the case of particles that have zero mass, such as photons which always travel at the speed of light, we find this short expression. The total energy is the sum of the rest energy and kinetic energy. The next example is very simple. To solve item A, we take the formula for rest energy and substitute mass and the speed of light. To solve item B, we calculate the Lorentz factor first and get the result of item A. To solve item C, we subtract the total energy from the rest energy. We now are ready to discuss the Einstein's iconic equation, energy equals mass multiplied by speed of light squared. Let's start discussing an elastic collision. Consider, for example, that two particles, A and B, with masses m sub A and m sub B, and their relativistic speeds as shown in figure, collide and emerge with masses and speeds as shown below. Let's apply the conservation of energy. Rearranging the terms, we can write this as the mass terms cancel each other out, leaving only the kinetic energy. That is, the total kinetic energy is conserved. Therefore, in the context of elastic collisions, relativistic energy conservation coincides with the familiar classical conservation of energy. We know that even in the context of classical mechanics, there are inelastic processes in which the total kinetic energy is not conserved. Let's see how an inelastic collision works in relativistic mechanics. Consider that two particles, Nb, with masses ma and mb, and relativistic speeds collide as shown in figure. They slam together in a perfectly inelastic collision to form one large particle at rest. Let's apply the conservation of energy. Rearranging the terms, we can write this as follows. The mass after the collision is larger than the mass before the collision. In other words, the mass is not conserved. If relativistic energy is conserved, as it must be, then mass cannot be conserved. Total energy can be conserved only if kinetic energy is transformed into an equivalent amount of mass. The first question is, why this such crazy idea was not discovered much sooner? To answer this, note that the last equation can be written as follows. The short answer to this question is c² is an extremely large quantity, so even if the kinetic energy is reasonably large, delta m is still very small, in most cases unobservable. The relation energy equals mass multiplied by speed of light squared is now believed to apply to all processes, although the changes are often too small to measure. That is, when the energy of a system changes by an amount delta E, the mass of the system changes by an amount delta m, given by. Probably the most well-known application of this formula is nuclear fission. Let's see an example. Uranium decays to thorium with the emission of an alpha particle. This is written as follows. To solve item A, we take the formula above and substitute the values. The mass of the parent nucleus is greater than the mass of the daughter nucleus plus the mass of the alpha particle. This released energy appears as kinetic energy of the alpha particle and the daughter nucleus. To solve item B, we must calculate how much of this energy will be carried off by the alpha particle. We know that momentum must be conserved as well as energy. Before disintegration, the nucleus can be assumed to be at rest, so the total momentum was zero. After disintegration, the total momentum must still be zero, so the magnitude of the particle's momentum must equal the magnitude of the daughter's momentum, and in opposite directions. You might be wondering why we are using the classical expression for momentum. We are using this expression because the velocities here are less than 40% of speed of light, so there are no significant differences. We now solve for velocity of alpha particle, and we substitute this value into the kinetic energy for alpha particle. Remember that the released energy appears as kinetic energy of the alpha particle and the daughter nucleus. So we obtain the velocity of the alpha particle